6th and 7th hour and anyone else that is listening to this recording. I'm sorry I couldn't be with you today, but hopefully this will help you understand Unit 5, Lesson 2, which is about complex numbers. The big idea that we've already kind of talked about is we can have quadratics that never ever hit the x-axis. So we need to come up with a strategy or some algebraic ways to deal with these kinds of quadratics. So if you think about what kind and how many solutions are there for each of these graphs, if I look at the first graph on the left, you'll notice that this graph is hitting in two spots. That means we have two real solutions for this quadratic. Now those two real solutions could be nice numbers like 5 and 7, or they could be irrational like 5 plus or minus the square root of 2. So when we say real, we don't necessarily mean that they're nice numbers, but they're real numbers. They're integers. They're irrational numbers. I could have 1/2 and 57/36. So those could be solutions. In the middle graph, you'll notice that we're hitting in one spot. So this is where the vertex and the x-intercept are the same. And here, we still have one real solution. Again, that real solution in this case is x is equal to 4. That's a nice, neat, wonderful spot. But you could have one real solution at root 3 or at 1/2. So remember, when we say the word real, it doesn't mean a nice number, but it is a real number. What we're going to talk about today are cases like in graph 3 where it never hits the x-axis. Therefore, we call this two imaginary solutions, which I know seems kind of weird. Why would we talk about an imaginary number system? But if you do kind of think about any of you that ever have to go to the doctor for your eyes and you need corrective either glasses or you need contacts, your optometrist or your ophthalmologist is giving you imaginary sight. Now they're giving you a contact lens or they're giving you glasses, but they aren't actually correcting your actual eye. They're giving you the gift of imaginary sight. And if you actually look at your prescription for eyeglasses, not contacts, you'll see them use eyes as part of their prescription. Okay, so imaginary numbers, like I just said, are used in optometry. And they're also used in electronics. If any of you have family members that are electricians, a lot of times they're going to use a J instead of an I because the lowercase I looks a lot like the number 1. So in electronics, sometimes you might see J. So we need to talk about the equation x squared is equal to -1. In the past, you couldn't solve it. If I would take the square root of both sides, there is no number times itself that gives me -1. So what we do is we define the square root of -1 to be the imaginary unit I. This is something you need to memorize. I is equal to the square root of -1. That is a fact. This is where we get it from. So again, an imaginary unit, sorry I spelled that wrong, I, usually denoted as a lowercase I with a dot, is equal to the square root of -1. So, if we know that I is equal to the square root of -1, then what is I squared? Well, I would square both sides, and by definition, isn't a square root and a power of 2, aren't those inverses that undo each other? So I squared is equal to -1. That's the only other math fact that you will need to memorize for today. So you need to know that I is equal to the square root of -1. Excuse me, I is equal to the negative square root. I'm saying that wrong. Pardon me, I'm teaching to like nobody in the class right now, so it's kind of awkward. I is equal to the square root of -1, and then I squared is equal to -1. So if you have to simplify with I, you should never have an answer that has an I to a power. Any I to a power can be simplified. So for instance, I is equal to the square root of -1, and we know that I squared is equal to plain old -1. If you have I to the third, you can think of it as I squared times I, correct? So I squared is negative 1 times I. We will not write this as the square root of negative 1. We would just write this as negative I. Again, when you simplify with I, you're allowed to have numbers like 1, negative 1, I, and negative I as your answer. You just cannot have answers like I to the third or I to the fourth and so on. You'll have to simplify those. Now, if I have I to the fourth, I can think of it as I squared times I squared, correct? Because 2 plus 2 gives me the exponent of 4. So this gives me negative 1 times negative 1, or 1. Okay. I to the fifth. Can't I think of it as I squared times I times I? I know that that is negative 1 times negative 1. So negative 1 times negative 1 is a positive 1 times I is a regular I. Think of I to the sixth this way. Can't I think of it as negative 2 raised to the third power? So that's negative 1 to the third. So negative 1. I know I'm going through this kind of quickly, but you just kind of need to sit and kind of think about it. I to the seventh, isn't that I squared to the third power because that's secretly I to the sixth? And don't I need another I? So I to the sixth was negative 1, so this is negative I. And hopefully you're starting to see a little bit of a pattern here. I to the eighth is I squared to the fourth. So when you take a negative and you raise it to an even power, you just get a positive 1. So when you're doing all of these bigger ones, I to the ninth, I can think of I to the ninth as I squared. Remember that base number that I have to know? To the fourth. That gives me 8 of them, and I need another I. So that's going to be a positive I, because I squared to the fourth is negative 1 to the fourth, and that's positive 1. I to the 10th is going to be I squared raised to the fifth, which is negative 1 to the fifth, or negative 1. When you're doing I to the 57th, I don't know that I want to keep doing this pattern, but I can think to myself, 57 divided by 2 gives me 28, and that gets me to 56, and I need an additional I. Well, isn't a negative number being raised to an even power of 28 going to make it positive? So this is going to be a positive I. If I do I to the 127th, same thing. Write down I squared. 2 goes into 127 63 times without going over, and then I have an I. But when I take negative 1 to the 63rd, that's going to leave a negative I. I to the 22nd is going to be I squared raised to the 11th power, and a negative 1 to the 11th power stays negative 1. All right, when you're taking the square of a negative number, this is what's important. You always need to take the i's out first. Take your i's out first. So if I have the square root of negative 3, you need to think of that as the square root of negative 1 times the square root of 3. So I get I times the square root of 3. We're going to replace the imaginary unit I for the negative 1. The 3 does not simplify, so it stays there. Okay? When I have I root 3 squared, this means I root 3 times I root 3. The I times the I becomes I squared. Root 3 times root 3 becomes root 9. I squared is negative 1. The square root of 9 is 3. And so I yield negative 3. All right, so when we solve a quadratic equation with I, here's the nice part. You know how to solve a quadratic. It's just that your answer is going to look different. So if I look at 2x squared plus 15 equals negative 35, because there is no linear term, I'm going to use square roots on this problem. So I'm going to subtract 15 from both sides. So I get 2x squared is equal to negative 50. Divide both sides by 2, so x squared is equal to negative 25. And when I take the square root of both sides, here's what happens, guys. I still get the plus or minus, but you need to think of this as the square root of -1 times the square root of 25. So I get plus or minus I 5, which is normally written like you would with a variable. Like I usually don't write x5, I write 5x. So I'm going to write plus or minus 5i. This means you have two imaginary x-intercepts or solutions or roots or zeros. In other words, this graph never touches the x-axis. When we go graphing next week, these are a little bit harder because we are going to have to t-chart some points out in order for us to figure out a nice graph with imaginary solutions. That's the only time it becomes an issue. So again, my final answer is plus or minus 5i. Okay. So let's try some more. Okay, when I have x squared plus 7 equals 0, there's no linear term. So I'm going to go ahead and I'm going to use square roots to solve this. So I'm going to subtract 7 from both sides. I have isolated what's being squared, so I'm going to take a square root of both sides. Again, the problem is I have a negative underneath a square root. So, sorry, this is not orienting well. That negative is the key for imaginary solutions. Mrs. Knopp is not going to, on a test, go, hey, everybody, remember when you have a negative underneath the square root, you have imaginary solutions. On your assessment, you're going to just be asked to solve the quadratic. And as imaginary solutions come up, you will need to know how to handle them. So think of this as the square root of -1 times the square root of 7. And I'm going to write this as the square root of 7i. Or, in this case, some students write I square root of 7. So it is very clear that the I is not underneath the radical. I'm going to go to example 3 with the same logic. There's no linear term, so I'm going to use square roots. So in order to use square roots, I have to isolate the w squared. So I have 5w squared equals -40. When I divide both sides by 5, I get -8. I'm going to take a square root of both sides. And again, ding, 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 the negative underneath the square root indicates I have imaginary solutions. Nobody is going to be giving you directions on a test that you have to use the imaginary I in the answer. So it's still a plus or minus, and I'm going to get the square root of -1 times the square root of 8. So when I break this down, I get I and then 2 root 2. And normally this is written 2i root 2. Again, it is not wrong to write it as 2 root 2i, but you need to make sure that you do not have sloppy handwriting because the I is not under the radical with the 2. If I have x squared plus 6x equals -10, it's your choice. In this case, I would not use the square roots because I have a linear term. You could see if it factored, but if I think about 10, the factors of 10 are 1 and 10 and 2 and 5, and there's no way I'm going to yield a 6. So you can complete the square or you can do quadratic formula. I'm going to complete the square just for the sake of review. So I have x squared plus 6x. 6 divided by 2 squared is 3 squared, which is 9. So I'm going to add 9 to both sides. Okay. And then remember, completing the square is a combination of factoring and square roots. So I'm going to factor the left side. And now I'm going to take a square root. And again, ding, 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 ding. I see a negative underneath the square root. So I get x plus 3 is equal to plus or minus I. And then in order to get my final answer, I need to subtract 3 from both sides. So I end up with -3 plus or minus I. Please be careful how you write this. It's plus or minus I minus 3 or -3 plus or minus I. It's not the plus or minus on the 3. This is the preferred answer. All right, so what is a complex number? Here's what I want to be clear on. What we were just dealing with were pure imaginary numbers. And I wonder if I have this written on the next slide. I sure do. So we'll talk about that on the next slide. But we're going to be dealing with operations of complex number. A complex number, a plus bi. A is the real number portion, and bi is the imaginary part. So it's very simple. When you're writing a complex number, the real number part must come first. Must by definition of a complex number. The imaginary part always comes second. So let's talk about all of the kinds of numbers that you have learned so far. All complex numbers are of the form a plus bi. So your real numbers do not have an imaginary number part. So a real number can be like -1, which is an integer. It can be like 5/2, which is rational. It can be a number like pi or √2 that is irrational, which is a non-repeating, non-terminating decimal. You can have a number like 5, which is a counting number. Okay? You can have a number like 0. Those are all of your real numbers. Pure imaginary numbers have no real number portion. So -4i, 6i, √7i, 8i. Those are what is considered a pure imaginary number. And then imaginary numbers have a real number portion and they have an imaginary portion. So 2 plus 3i. The 2 is the real, the 3i is the imaginary. In 5 minus 5i, 5 is the real, -5i is the imaginary. So when you add and subtract complex numbers, it is not difficult. Problem A here is the one that kids miss the most because of this pesky subtract. Basically what you end up doing is, when you add or subtract two complex numbers, you add or subtract the real number parts and you subtract their imaginary parts separately. So when I have 6 plus 3i minus 4i minus I recommend that you distribute the negative. So I have 6 plus 3i minus 4 plus I. I know that's an extra line of work, but it will save you. I add the real number portions together to get 2. I add the 3i, or the imaginary numbers, together to get 4i. And that is my final answer. 4i plus 2 is not acceptable because a complex number comes of the form a plus bi, where the real number part is first and the imaginary is second. When we go to B, again, this should hopefully be a pretty easy problem. Because of the plus, you don't have to worry about distributing anything. 2 plus 7 gives you 9. 5i minus 2i gives you plus a 3i, and you're done. Life is good. All right, now we're going to multiply complex numbers. Basically, in a nutshell, you have to FOIL this problem out. Okay, you treat it just like you would x plus 3, x plus 4. Exact same way. The only difference is we are going to have to simplify I when we're done. So when I do my first, 2 times -5 is -10. When I do my outer, I get a plus 4i. When I do my inner, I get a minus 5i. When I do my last, I get a plus 2i squared. I can combine those terms. So I have -10 minus I, but remember my simplification rules for I. I cannot have a power other than 1 on an I. I can simplify to -1, 1, I, or -I. Well, I squared is negative 1. Yes, I might be writing out more steps than some of you need, but I'm not here, so I want to be clear. So negative 10 minus I minus 2. So I am left with the real number portion, negative 12 minus I. And I know this is kind of abstract. It's theory. You're like, what am I doing? You're just doing operations with a new number system. The conjugate applies. So this problem, if I gave you 6 plus 4i over 2 plus root 3, wouldn't we multiply the numerator and the denominator by the conjugate of the denominator? So this is a parallel problem. That's exactly how we're going to treat this problem. If I have 6 plus 4i over 2 plus I am going to get rid of the I in the bottom because remember, this represents a square root in the denominator. And if we want this in standard form, we don't want i's in the denominator, or we don't want i's in the denominator or square roots. So I'm going to multiply the numerator and the denominator by the conjugate of the denominator. Remember, this is truly the number 1 in red that I'm multiplying by. I'm just representing it as 2 minus I over 2 minus I. So the denominator you can flip. The denominator is going to be 4 minus I squared because the positive 2i and the minus 2i are going to cancel. But you have to FOIL the numerator. You cannot just blur that. That's because they are not conjugates. So my first is 12. My outer is a minus 6i. My inner is an 8i. And my last is a minus 4i squared. Again, I'm going to do this in steps. Okay, so you might not need all of these steps, but I just want to have clear work. Okay, in the numerator, I can combine those terms. So I have 12 plus 2i minus 4, and I squared is negative 1. In the denominator, I have a negative 1. So then in the numerator, I have 12 plus 2i plus 4 over 4 plus 1. So I can combine the real number parts to get 16 plus 2i over 5. And just like we did earlier, this is simplified. This is full credit. Or I can do 16/5 plus 2/5 I. And this is what we mean by standard form. Standard form of an imaginary solution is a plus bi. A distinctly separate real number portion and a distinct separate imaginary portion. So this is my real portion, and then this is my b, and this is my I. So this is what we would be looking for if we have an answer in standard form. All right, we're going to plot the complex numbers in a complex plane. I want to be really clear with you that these are easy. However, to be clear, this is not a real number XY coordinate system. We are defining the horizontal axis to be your real number portion, and we are defining the y to be your imaginary number portion. So if 4 is the real number portion, 1, 2, 3, 4, this is where I'm looking at. Okay. The 3i, I'm looking at 1, 2, 3, so right around here. So in order to figure out my point, I want to know where those meet. So this point right here is the coordinate 4 plus 3, or the number, not the coordinate, excuse me. That is the point 4 plus 3i. When I want to do negative 5 minus 4i, I count down 1, 2, 3, 4, 5 on to the left, and that's not the actual point. You just can't see what I'm doing with the pen. So I'm doing 1, 2, 3, 4, 5, and then I'm going down 1, 2, 3, 4. So this point right here is the point negative 5 minus 4i. So if you're being asked to do the absolute value, I'm actually going to do a new page because this is our last slide. Let's talk about the absolute value of 6 minus 8i. I teach a little bit different than this slide. I think hopefully it'll be a little bit easier. Okay, so if I want to do, let me see what the problem was. If I want to do the absolute value of 6 minus 8i, I'm going to plot it first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So I'm right here. Okay. If I want its absolute value, doesn't that mean its distance from 0? Okay. So wouldn't that distance be this? So what I can create, guys, is a right triangle. Where this was a distance of 6, and wasn't this a distance down of -8? I know this represents the imaginary axis, and this represents the real axis, but ultimately, kids, you're trying to find this distance. This right here is your absolute value of 6 minus 8i. So in order to do that, guess what? We use Pythagorean theorem. 6 squared plus -8 squared equals c squared. 36 plus 64, that's 100. We're talking about distance, so even though you technically do get a plus or minus 10, in terms of a distance, in the context of this problem, my absolute value is equal to 10. Let's say that I wanted to do, what is the absolute value of 5i? Well, 5i is located on the imaginary axis. Let me go down. 1, 2, 3, 4, 5, right here. Well, what is that distance from 0? It's a distance of, you know what? Hold up, wait a minute. I'm not recording this because I messed up. Hold up, hold up. All right, so I have the absolute value of 5i. I went down. That was a major malfunction. My apologies. So 1, 2, 3, 4, 5. This is where 5i is located. And if I look at its absolute value from the origin, that's just 5 units. Let's do one more. Okay. If I wanted to do 2 minus 3i. Oh, let's do plus. Let's put it in the first quadrant. All right, so I would go 2 on the real, up 3 on the imaginary, which puts my point here. That's my distance from 0. And here is my right triangle where I have a distance of 2 and a distance of 3. So I would do 2 squared plus 3 squared equals c squared, which is 4 plus 9, which is 13. So its absolute value is equal to the square root of 13. So notice how the distance is not imaginary. The distance is real from a complex number. All right, friends. So I have a packet that the sub should have, or you could have printed it off from the internet. Packet 1.5, only do the odds. And then that is going to, this is going to be all of your operations with complex numbers. Then you need to go back to 131, and you need to go to 65 to 73 odd and solve some equations that deal with imaginary solutions. Now, this is a video, and I'm almost done, but my hope is that I will have this on YouTube. So if this was too fast for you in class, I have the 3 desktops on the side of the room. Put your headphones in and feel free to rewatch it by yourself. If any of you can get this YouTube video on your phones, this is the one time where, provided that I'm being crystal clear on this, you have to be watching your math. But if you need to rewatch this video, please feel free to do so. And yes, you are going to have a daily assessment over this assignment next Tuesday when I see you. But I am here on Monday before and after school and Monday morning or Tuesday morning. So if you have any questions, come and see me. Feel free to email me. I am out of town this weekend, but I should be on email Sunday night. So hope you enjoyed. Hope this helped. It's not that hard. Hang in there and have a great weekend.